everyone, good morning. Hope you are enjoying CppIndiaCon 2024. So I'm Mahendra. I will be talking about undefined behavior in C++. So this is the agenda of today's talk. So we'll go with some definitions from this standard, what is meant by undefined behavior, unspecified behavior, implementation defined behavior, and other stuff. Then I have categorized UB into some couple of broad categories. We'll go through that. Then we'll go through that how compiler sees your code when there is undefined behavior. Then we'll talk about why standard chose to have undefined behavior. And at the end, I have a couple of slides to talk about how to avoid or detect UB. Even the intention of this talk is not to go into the details of avoidance and detection of UB. That can be a totally separate talk. But I have some couple of slides there. And at the end, we'll have Q&A. Okay, so let's start with the definition. So what is meant by a defined behavior? So C++ standard defines something for a particular operation, and it is explicitly defined, explicitly specified. So we call it as a defined behavior. So if there is an operation which is a particularly defined, then compiler has a responsibility to generate a sensible code for that one. Very simple example is adding two integers. It is predefined that adding two integers is arithmetic addition. Then we have, let's say, another example here, lifetime extension. We know that even though std string is going to get destroyed here if we don't bind it with the const reference, but C++ standard allows that if it is bind with the const reference, then the lifetime should get extended. So this is we call it as a defined behavior. And most of the time, 90% of the code we deal in the defined behavior scope. Then what is implementation defined behavior? So the behavior where implementation makes a difference. For example, it can be some hardware. For some embedded hardware, the size of integer can be 32-bit, but for x86 64, it can be 64-bit. Another implementation defined behavior can be a null pointer representation, let's say. Standard says that, okay, if null pointer is compared with the 0 value or the null macro, then it should result into a true. But it doesn't specify that what value actually null pointer contains and what is that exact value. In some platform, it can be 0x00, and some platform it can be 0xff, or on some other platform it can be some anything. But whatever is that implementation behavior, that behavior needs to be documented. That choice must be documented. What is mean that if I am executing this program on x86 64 machine, and then it is documented that what is the size of integer. Okay. Then there is something called as unspecified behavior. It is exactly like an implementation defined behavior with only one difference. Here, there is no compulsion to document the choice. Okay, a standard might provide some multiple options, or it might not even provide, and the platform might choose to take one of that option, and it don't need to document that one. So that's we call it as an unspecified behavior. One of the example here is the order of evaluation of function arguments. I mean, some platforms you will see it is left to right, some right to left, but standard doesn't guarantee what it is. Again, all these things keep changing with the C++ standard. Earlier, let's say whatever was undefined behavior, that might come into unspecified behavior. Because of change in the standard, undefined behavior moves from undefined behavior to well-defined behavior. So example might vary based on the standard. Now, this is very curious case. I mean, you might have seen, people don't talk about defined behavior, implementation defined behavior, but people talk about undefined behavior. So what is undefined behavior? So behavior for which C++ standard doesn't impose any requirements. So if C++ standard doesn't impose any requirement, then compiler might choose to do anything. It might, your program might fail to compile on particular GCC version, let's say, and it might compile correctly on the next GCC version. It might execute correctly, whatever is the intention of the programmer, and you will be like, oh, I'm happy that my program is executing correctly. But there is slight change in your program, and your program style will start misbehaving. So that is an undefined behavior. So you can't guarantee what will happen. And we'll see some examples, very shocking example or very curious example about this. One of the example about this is like a dereferencing a null pointer. And most of the people have assumption that if you do a dereference a null pointer, then it will lead to a crash. But in reality, dereferencing a null pointer is an undefined behavior. Okay, this is some common categories of undefined behavior. This is nothing standard. This is what I thought and I have put into different buckets. One of the major categories about which people talk, about which people curse C++ is this memory access related UBs. What are that? Basically, you are accessing a memory which you suppose you should not to be. For example, there is null pointer or dangling pointer, going out of bound access, double or invalid free. What is meant by invalid free? Let's say you allocated a pointer using a malloc, and then you are trying to delete it using a delete. So something like this. Misaligned memory accesses. For example, you have some array of uint 8t, and then you are starting to access the memory from the second element for uint 64t, and the second element might not be on the boundary of let's say 64 bits. So this is nothing but misaligned access. Some platform will allow misaligned access, some will throw an exception, some will return some garbage values. So we don't know about it. Another category is a control flow related. These are some of the categories. For example, reaching the end of non-void function without return. Again, there is a lot of assumption when I talk to a lot of people. They say, okay, if I don't put a return statement, then compiler gives me an error that there is a no return statement. But that's not true. Compiler might give just a warning. That is also in some cases, or let's say nowadays, most of the cases, but it's not mandatory. So if you have some function and you have non-void return type and you don't return, then it will create a problem. I think I have one example of that as well. Or let's say calling functions through invalid function pointers, basically using C-style casting to cast any pointer to any other function pointer. Infinite recursion is another example. Returning a reference to a local variable is another example. Then concurrency related, basically data races where you're trying to access or modify some memory through two different threads. Improperly managing the thread lifetime. For example, thread is detached or it is terminated. You're still trying to do some operation on that. Double locking mutex on the same thread. So that might lead to some undefined behavior. The another one is, this is again interesting category, which is operation related. What is operation related? For example, signed integer overflow, addition, multiplication, very simple operations. Or shifting any number by negative or excessive amount. For example, shifting uint 32t by 32 times, right? Division by 0. Again, some platforms, I will say, might trap division by 0 and throw an error. Some might just ignore. Sometimes compiler might just say, okay, there is a division by 0 error, 0 happening. This is undefined behavior, and let me do some optimization there. Or modifying a value more than once between a sequence point. For example, I is equal to I plus I, right? Something like this. And the last category here is not last, the second last, API misuse related categories, where basically there is an object and it is not in that valid state where you can call a particular API. That API has some constraint. For example, you have a std vector and you're trying to call subscript operator with passing some value which is going out of bound. That is not in that state, so that can also be a UB. Or let's say you're trying to access you're trying to cast std right, to a type which is not the exact type. Or let's say accessing non-owning view after the underlying object is destroyed. For example, there's a std string view which is the underlying object is std string and that got deleted and you're still trying to do some operation. Now it is in not that state. So that is a API misuse related category. And the last category which we have is a platform or environment related category. What is this category? Basically, we say that, okay, we are assuming something that, okay, this is the Indianness of this program where I will be working on without checking Indianness and then doing serialization, deserialization operations. That might lead to undefined behavior. Or for example, size, written a code which let's say works on multiple platforms, and I'm thinking, okay, the size of int will be 4 byte, and according to that, I'm doing some operations that again can create a problem. Let's say improper file handling, opening a same file handle in a basically one in a read mode, one in another write mode, or third in a write binary mode. So such things can cause a undefined behavior. Okay. So now from here, we'll see some examples from the compiler's perspective, that how your compiler see your program and how does it detect undefined behavior. Before going into that section, what I want to do is categorize any of our code into 3 categories. The first category is, let's say, well defined for all the inputs. So compiler can prove that, okay, there is a no undefined behavior irrespective of the input. Then it will generate the sensible uh, uh, code for that one, sensible assembly instructions. The second category is undefined for all the input, which is I have given it as a type 3. Here, the program is doing some nonsense thing, some silly thing, and the compiler is not even interested to that. The compiler can just throw away that, because compiler can prove, okay, it is undefined behavior at the compile time itself. But the most interesting is this third category, which we are calling as a type 2, which is in between, and that's where majority of the bug lies. Undefined for some of the inputs and defined for some of the inputs. For example, let's say take very simple example of addition. Now adding two number, there is no undefined behavior here for most of the inputs. But for some of the input, it might lead to undefined behavior because of the overflows. Accessing, let's say, vector, right? If unless I mean till you are accessing within the bound, there is no undefined behavior. But as soon as you try to access out of bound, then you are into undefined behavior space. So these are mostly runtime undefined behavior, I will say. This categories I have taken from one of the blogs, so they have given a reference here. But this make our life easy to, when we'll see the example that how this category is related, how compiler is treating these categories differently. Now, before going to, from the compiler's perspective, I will be going to show you some assembly instructions and all these things. So I just wanted to, have some basic understanding here. So just remember that whenever we see RDI, RSI, RDX, RCS, R8, or R9, these are some general purpose register which are used to pass arguments to different functions. So where the RDI register we pass as a first argument, RSI as a second argument, RDX as a third argument, and so on. So first 6 arguments will go into this, and later all other arguments, if we have, will go on a stack. The function always returns a result into EAX. And for example, if we have structure, might be its reference or pointer address will return into EAX. If it is actual value which can fit into EAX register, it will come into the EAX register. Okay. Basically, EX is a 32-bit register. Similarly, you can say it is an RAX register, might be if it is a 64-bit value. Similarly, ESI and EADI holds the 32-bit values of the 64-bit register. So if there is some 32-bit operation is happening, compiler might, instead of generating RDI register, it can generate the ESI or EDI registers. Just keep this in the mind. I mean, even if you don't keep, I will explain when I'm talking about the code. So let's talk about this code. Very, very simple code. What we are doing here is we have a main. In that main, we have infinite while loop. Below that, we have this code unreachable function. You can give any name, and we are printing, okay, CppIndiaCon 2024. Now, I will go to the audience. How many of you say that, okay, this program will crash, or let's say, because we have infinite, or it'll crash, or it might go into infinite. I'm just waiting for your answers on chat. Okay, got one infinite loop going into infinite. Okay, it won't crash, we'll go into infinite. Okay. Okay. That's what I expected, but that's why I have example here, because it doesn't go into infinite loop, because infinite loop without any side effect is undefined behavior. So here we don't have any side effect. So if I run this code with a particular compiler, with a particular setting, I get CppIndiaCon 2024. I'm running this code with the CLang 18.10 with -O1 optimization enabled. Okay, how? I'm not calling unreachable here, right? I mean, what is happening here? Okay, so let's see how compiler is treating this code and what it is trying to generate out of this. So what does basically, I will go to the last slide. What does basically compiler thinks that, okay, programmer are, you know, they are very clever. They will not introduce undefined behavior. So when they are seeing this while true, and the compiler thinks, okay, I mean, it can't be a here. This is undefined behavior. Something wrong is happening. So let me do something. What I will do basically is I will delete this code. I'll just delete this code simply. And if you see, this is the actual assembly which got generated. And you see there is nothing generated below main label. And what it is doing basically is after that, okay, if there is nothing generated to main label, your C runtime or C++ runtime, whatever is the runtime, will call main. It will come to this address, but that address is exactly as addressed to the this next code, which is unreachable code. Okay, because there is no instructions there, so there is address there as well, and then it will start executing this push instruction. Well, forget about this push move LEI instruction. There is this next move instruction, which is nothing but this. What this instruction is doing, basically, it is moving 17 to this EDX register. And as we talked earlier, EDX is a first or second parameter. Okay, EDX is a first or second parameter to this function call, whatever we are doing. And then after that, we are calling stdc out, which is nothing but some operator overloading, and we are passing 17 there. What is 17? If you carefully calculate, the length of this string is a 17. So what it is trying to do is basically calling stdc out to do this print and whatever this address we see here. You see here, this LEA instruction is loading address into this RSI, and at the end we get CppIndiaCon 2024. And this is what it happens. All right, and in real time it's happened. We have seen such an example in our code base. Again, this is a very simplified example. We have seen this code that there is some infinite loop and it is calling some function which was never called. And you imagine how difficult it is to debug, right? I mean, you put a breakpoint, and in breakpoint you see, oh yeah, the code is coming from there, from some particular location, but I'm not calling that one. Okay. So this is one example of undefined infinite loop. Okay. I will go a little slow. Okay. Now let's take an example of this sign integer overflow. Very, very simple code. What we are doing, we have defined one function called as a check overflow. I'm using a fixed integer, fixed width integer types here, because just to make sure that, okay, I'm dealing with the 32-bit values. What I'm trying to do to check overflow, I'm doing a plus b if it is less than e. What I am assuming is, okay, I'm developing this code for x86-64 machine, and when it will do addition, it will use the add instruction, and when it will do add instruction, the wraparound will happen. So if it is an overflow, then a plus b will be a less than e. This is what I am being over smart, right? I'm trying to think, okay, what compiler is trying to do here. And then I have another function add, which basically calls the check overflow AB. And if it is overflow, then I just return 0. Otherwise, I return addition. Now, how many of, okay, sorry, it's still. Now, this is code, let's say I'm using this code in the main function or somewhere else I'm calling. So I defined A as a variable where I am taking a maximum representable value of E32T, which is 0x7 followed by FFs. And then there is another variable I have taken B, whose value is 1. So if we add 1, then the overflow will happen. All will become FFFF. So now if I do stdc out of add A, comma B, what should be the output? Okay, if you have any questions, put it into Q&A, because then I will miss it to read into the chat. Okay, so please put into your, okay, -1. Okay, we can talk about hex as well. It can be 0 xff. Okay, but okay, 1 is -1. 0. Okay, 0 ideally. Ideally, it should be 0. That's what we are saying, right? If it becomes negative, let's say a plus b becomes a negative, or let's say when a plus b becomes a 0, it will be less than a. Then check overflow should return a true, and then it should return a 0. That's what the understanding, right? At the end, because we are doing the same operation here, a plus b, and here also a plus b. But here is a shock. It is a negative value. Why? Even though we are checking here, now if you see a plus b, the written result is minus, and which is checking less than a, everything is integer, then why? What is happening here? Okay. So let's take a moment and try to analyze this program piece by piece. So we have this function check overflow, a plus b less than a. Now again, compiler is a smart enough. What it says that, okay, programmer can't do a mistake. So a plus b less than a. So a plus b can't overflow. That's what the assumption of the compiler, because it is undefined behavior. So as a plus b can't overflow, there is only one condition where a plus b can be less than a. What is that condition? When b is negative. Right? If b is negative, then it will go like it will have to subtract from a. So it will become less than a. So compiler thinks there is only one possibility here. If the b is negative, then only a plus b less than a will become true. In other cases, it can't be, because programmer is smart and he will not introduce a undefined behavior. And that's what compiler does. What it does is basically, here you see the first instruction, basically we are moving this ESI value to the ESX, and which is nothing but our second argument, which is nothing but B, which we passed as 1. And then there is a shift right instruction by 31 times, and the result will be stored in EAX. So if it is 31 times shift, then the last bit will be in the EAX. So if the value is negative, the EAX will contain 1, which will be interpreted as a true. If value is positive, it will be treated as a the 31, I mean the last bit, which is the 32 bit, will be a 0, and it will be treated as a false. This is what compiler is doing, and that's what is happening in this particular case. Okay. So in nutshell, compiler has optimized this code like this, right? And that's why we see this problem. Okay. So if you have any questions regarding this one, please note down the slide number and put it into Q&A. We'll come back to the questions. Now coming to next slide, which is nothing but signed integer overflow inlining. Okay. Till this point, what we were assuming, whatever the check overflow function is there, it is sitting in some another translation unit. So inlining is not possible. Now let's assume that check overflow, the compiler is able to see through the definition of check overflow. So it can see, okay, what you are doing. Basically, there's a very simple operation it has to do. So instead of calling a function, it will basically do inlining. And let's see what compiler tries to do. Okay, you see here there is no call to check overflow, and there is no shift right instruction as well here. So when you assume that inlining, it doesn't mean that the assembly will get copy pasted here. The assembly will totally generate, and this is like when we say that, okay, inlining creates a scope for more optimization. This is that case. So what is happening here once again? Check about this instruction XOR EX into EX. So in EX we have now 0, right, on this instruction. Now what we are trying to do here is we are trying to do test ES and ESI. What is basically this test instruction does? It does bitwise AND of this ES and ESI. But instead of storing the result, it checks some properties of the results and sets some flags of the CPU. What are that flags? It sets some whether sign bit is set after doing this AND, or let's say whether the result is 0, all such. And in this case, let's say it is majorly interested in to check whether the sign bit is set. So if you are doing an AND operation with, let's say, the number itself, then the result will be that number itself, right? So let's say 100 and ending with 100, we'll get 100 only. So if the number is a negative b, then the sign bit, because we x86 again talks in terms of 2 bits complement, so last bit is a sign bit, will get set to 1, and this instruction then will set some flag called as a sign flag into a compiler in the CPU. And there is this next instruction again, which is a very optimized instruction. What it does is basically, this is called as a conditional move. So what I will read it like, C move means conditional move. What is condition? When the sign bit is not set. So if the sign bit is not set, then you basically move this result of ECX to EX. Now what is into ECX? See, ECX is nothing but addition of RDI and RSI. Again, if you see compiler is not using add instruction here, you want to do this addition of A plus B. This instruction is called as a load effective address. So it is basically treating this integer as addresses and basically trying to add them and load them into ECX. So don't assume that for addition, compiler will generate add instruction only. Right? It can generate any other instruction depending on the optimizations, and compiler will know that, okay, how many cycle it is going to take and all that scenarios. So again, RDI and RSI, as I talked, RDI is nothing but ESI. Sorry, RDI is nothing but 64-bit value, and RSI is nothing but a 64-bit value. But again, we just have zeros into the upper 32-bit, and the ECX will contain only the 32-bit value. And at the end, we'll, if the B was negative, then the result will go into EAX. Right? So the result will go as A plus B. If it is not negative, sorry, if it is not negative, then result will go as A plus B. Otherwise, the result will go as a 0. And that's why this is what basically it is trying to do. Okay. Okay. So, I'm just taking a pause for a second here so that you can look through that what it is trying to do here. This is nothing but int32 result is equal to A plus B, which is nothing but this LEA instruction. Then it has created this, let's say, another variable for storing 0. And then it is checking if B is less than 0, then basically return a 0, otherwise return a result. That is what all these things is doing. Okay. Coming to next example, right? I told, right, we have some example about a null pointer dereferencing. So we assume, what we assume, that if we have a null pointer and we reference, then it will crash. Okay. So let's see this example. Let's say we have this class called as a processor, and then we basically have a constructor which takes some seed value. Then we have another function process which takes another uint32 value. It does some processing and returns a result as uint32. Now, okay, I will start with, let's say, in this case, first case, okay, let's say I don't define constructor. Okay, process is defined. There is a definition available for this one, but there is no definition available for processor. Will it compile or not? Here my question, once again, I'm telling you. The definition of process is available, but the definition of processor is not available. And I am trying to use in this way, will program compile? Okay, in most of the cases, we have seen that, okay, if you don't have a definition, it will compile, but the linking error you will get. But in this case, you will not get a linking error because we are not constructing any object. We are not, basically calling the constructor of processor. So even if it is not defined, it's fine. Compiler just ignores it, right? Now we are calling this PB as a process on 10. Okay. And let's see what is happening here. Okay. We'll go one by one. So whether this will crash or not crash, it depends actually on what is inside the process. Okay. How that I will talk about it. There is no direct answer here. Okay. So let's say if the process function is doing return x into x, then whether it will crash or not. Okay, yeah, it won't crash. Why? Because we are not referencing this pointer here, right? Correct. We're not referencing this pointer here. So it perfectly passes, right? And then people say, oh, okay, it's working fine. And then they add some variable into that code, let's say like this, and say, no, now my program is crashing, right? Okay, this was a simple example. We were able to see that, okay, there is a null pointer and then people say, no, when I'm trying to reference the seed, then there is a problem. Might be there is some memory corruption or there is something happening, some magic is happening. Why? Because program is crashing. Correct. And you might have seen that, okay, you add one variable and your program start crashing, and that is a symptom that your program has a undefined behavior. Again, this is tested with GCC 14.2. If you test with CLang, you might get different result. If different versions, it might get a different result. Okay. This is the problem with the null pointer differencing. Okay. So this is the basically the code. What is happening in this code is we'll go piece by piece. So if you see here, when we are creating a null pointer here, then somewhere before calling this process, this is the first argument. So first argument to functions are actually in the x86 ABI context is this pointer. So here it is a null pointer. That's why we are doing XOR of EDI into EDI. So the EDI will contain 0, which is nothing a null pointer. And then we call second argument is as 10, which is passed to ESI. And then we call this process function. And then process function does something. And then basically we have something into result into AX. And then we are moving into ESI basically due to the C out, all this below thing is done, right? So we'll not go into that part. So, but this code is for a C out. Okay. What happens? Basically, when you are doing X into X, basically here, once again, you are moving the first, whatever the second argument into the EX register, which is nothing but a result register, and you are doing a multiplication, I multi, right? Because you can't have 3 operands in the x86 IML instruction. So basically, it will do EX is equal to EX into ESI. But when you have this seed value here, now see how the assembly is getting changed here. This is remaining the same, but we are doing some addition. In the add, we are basically doing D pointer, RDI, and all these things. Not getting into the details. Once again, if you remember, RDI was nothing but our first argument. It's nothing but this pointer. And in the class, we don't have any other variable. So most probably the first word will be the seed value. That might be the layout. That's why it's just loading the first word and then adding that into EAX. That's, no, don't get into the details, but we are trying to dereference here the pointer, which is nothing but a RDI. So this is basically we are trying to reference the 0 memory now. So we get into a crash. Taking a pause here. So can digest this. Okay. So when we do a inlining, once again, some interesting things will happen. Compiler will be able to see through that, okay, you are doing something which is undefined behavior. So it will be able to see, okay, I'm passing a null pointer. This is going into process, and the process is basically trying to have this seed, trying to use the seed value, which is nothing but through the null pointer, which is nothing but undefined behavior. So this complete function is undefined behavior, the main. So if it is a complete function is undefined behavior, then I don't need that function. I will not generate any code for that one. So if you see below main, there is nothing generated. You are trying to fetch a code from somewhere else, and then the program terminates. Okay. See, because compiler was able to see that there is undefined behavior into the process. See how it is propagating. There is undefined behavior into the process, and also undefined behavior because we are trying to dereference the null pointer. So all these things is going for a toss, and main is not getting generated here. Okay, let's go to last example of this session. So we'll talk about this simple finite loop. Again, this is I have taken from one of the blog, which is first time it is reported to GCC by Eric Muser, and I have taken the code snippet as it is. So what we are trying to do here is basically there is some buffer, and that buffer we have some character string y, and then we are iterating from j0 to 9, and then we are doing some computation and multiplying the value of j, and this last value, whatever we have written here, the significance of this buffer is just to avoid some unnecessary optimization, because we want to focus on what is happening with this loop and this STDC. Now, how many of you think that this loop will terminate? Be honest, don't tell because you have to tell it another answer, because it is a talk on undefined behavior. How many of you think this will terminate? Okay, not waiting further. Yeah, it doesn't terminate. That's why I have taken this example. Ideally, it should terminate, right? I mean, if you see, we'll not go into the definition to check whether the the loop terminates or not. J is from 0 to 9, very well defined, which integer is like, can have value 9, can hold value 9. There is a no undefined behavior here. Why? What is problem? Okay. So if I run this program with GCC 14.2 with O0 optimization, it returns some garbage. I mean, it prints this, but it terminates. Okay, we are happy with that. We know that, okay, there is an overflow happening into this multiplication. We are okay with this overflow. But loop is terminating. But if I increase the optimization level to 1, then it starts throwing me some warning that there is some undefined behavior here, and it goes into infinite loop. Okay. It doesn't return this one. These are just warning, and it goes into infinite loop. How it goes in, we'll see that one. If I level up one more time the optimization level, I don't even get a warning that there is some undefined behavior happening. I just straight away get like in infinite loop. Right? At least with O1, I was able to get some warning. And again, this keeps changing by version to version. With version GCC below 14, I think we were not even able to get a warning. With 14, we were able to get a warning. And whatever the optimization happening, it was that time was available. This was available only with O3, because there is aggressive loop optimization happening here. Let's see what is happening here. Okay. So this was our code. Okay. We have trimmed down main function and everything. And then what we are trying to focus is on this for loop. Very simple for loop. What compiler thinks is, compiler is, again tries to do some optimization. What it checks, okay, I am using J just to do a sum computation. I'm not using this J at any other place. So instead of comparing on a J, why not I do a computation, and on that computation itself, I do a check, so that I don't have to increment J, I don't have to waste the register to store the value of J and all these things, right? So what does it do in the aggressive optimization? It basically creates this variable P, which is nothing, start from 0, because if you multiply with J is equal to 0, the result will come as 0. And it is less than 9. So P is less than 9 into multiplication of this, the P plus, and every time we are incrementing by this value. So this is the first level optimization compiler has done. The compiler doesn't do just a one level optimization. It goes to multiple ways or multiple loops to do optimization. And in the second loop, it says, okay, now let me see this condition. And this condition is basically 9 into multiplication of this one, which will result into overflow, which can't happen. Okay, if this can't happen, that means this undefined behavior. And then, okay, let me mark it as a true. Okay, so compiler completely eliminates this check, P less than 9 into multiplication. It just basically says, okay, it's undefined. So basically it's a true, always true. Okay, so that's why we basically get into this infinite loop and all these problems. Again, this is because of the optimization. Now, just to point out, whatever analysis we have done, that analysis I'm not doing just to tell you that, okay, if you do something like this, then this will happen, or if you do like PQR way, then XYZ things will happen. What I am trying to say here is when there is undefined behavior, you don't know what will happen. So don't rely. If your program is executing, I mean, people come to me and say, okay, I have undefined behavior. What is the problem? My program is working. Yes, your program is working today on your machine. It might not work on someone else's machine. It might not work with some other compiler. It might not work when you do some changes in your code. It might not work when you increase your optimization level. At the time of debugging, you might see a different behavior. At the time of, in the production environment, you might see a different issue. So if there is an undefined behavior, then this is a symptom of incorrect program. So fix that one. Okay. But then what is the problem with the undefined behavior? I mean, we have something called as unspecified behavior. We have something called as implementation defined behavior. We don't talk about that much about those categories, but we talk about undefined behavior. And in program, we might also have these logical errors and all these things, but we are not talking about it. Why we are talking about undefined behavior? The problem with the undefined behavior is that it sometimes works, sometimes doesn't work, and it can come in a future. And when it comes, you don't know that what has changed to come into this stage, right? And we say that okay, there is some regression happened in last release, it was working fine. I haven't done any change related to this module, nor I have changed any single line in this complete file. Still, there is a crash in my code. So that is the problem with the undefined behavior, right? That it manifests in some later stages. Okay, we have talked about a lot of bad things about undefined behavior, but is there anything good about undefined behavior? Okay, after showing all this example, you will ask, okay, are you kidding me? What good can be about undefined behavior? Undefined behavior, I will say, makes C++ compilers efficient to generate a more efficient code. Right? I mean, because of the undefined behavior, compiler can say that, okay, this can't happen, so I don't have to check all these things. For example, array bound can't go beyond, let's say, that limit. That is what the invariant I am putting. So if that invariant I am putting, I don't have to check that one. I don't have to generate that instruction. And that might be, generating that check might be fine for when we are running on x86 machines. We have a very good computation power, but it might not be good when I'm, basically that one single instruction might be a problem when I'm running in some very tight critical loop, doing some communication, some signal handling, right? That one instruction might be a problem for me. So I don't want that extra head. I might want to be more careful, right? So that's why C++ gives you, I mean, way that, okay, that can be gone in both the way, wrong or right. Okay, so we have undefined behavior in the standard. Why we have undefined behavior in the standard? Why we don't say, okay, we'll remove all the undefined behavior and we'll make sure that everything is defined? There are one reason which I talked about, performance considerations, because C++ is used in wide variety of platforms, right? So you don't want to do that one for particular things. Again, complexity and implementation challenges. There might be some situations where proving that whether it is undefined behavior or not might be a challenging itself. So we want to keep language simpler, want to keep compiler simpler. Flexibility for hardware platforms. Again, different hardware platform might want to treat different operations differently. For example, misaligned accesses in x86 might be different, in ARM might be different, in AMD it might be different, right? So we don't want to enforce something on hardware. So that is another reason. But yeah, I completely understand, and there are reasons. For example, the one which we saw in infinite loop, compiler can detect, okay, there is infinite loop happening, there is undefined behavior happening. So it's responsibility of the compiler, I think, to give us a warning, to give us an error. And compiler is doing a really good job as compared to, if you compare in last 5, 6, or 10 years, compiler is becoming very good in giving warning and error. Okay. This is one slide. I have kept it as backed up, but if, as the time is permitting, I will talk about this. So this is again relation. What is the relation between UB and const expr? And you might be saying, okay, I jumped from UB to const expr. So this is one of the technique by using which you can avoid basically undefined behaviors. How? See, const expr get evaluated at a compile time, and what standard says const expr expression, whatever it is, it can't be an undefined behavior. So if I have this code int get element, very simple code, and I am this having an array of size 3, and I am trying to get element at fourth index, which is again undefined behavior. But if I execute this code, this might return some value to me on a particular platform on a particular day, or it might return a 0. Again, it depends on my luck. But if I mark this function as a const expr and this value as a const expr, what it tries to do, it tries to evaluate this get element function at a constant time, at a compilation time. And at that time, it says, oh, there is an undefined behavior here. Okay. Again, this is very simple example. This is very toy example, but there are nice blogs written on a const expr and its interaction with undefined behavior, and that how you can make your program more safer. So if we can put a const expr at a particular place, go and put a const expr, because it might be able to detect some undefined behavior, and it detects that, okay, this is outside of the bound, very clear error here, and compiler doesn't compile this program. Okay, this is last set of slides on how to avoid or detect a UB. Again, not getting into the details, not showing any example. What you can do, you can use same programming practices instead of assuming something. I mean, I have seen in a code which is like a production code, there are uninitialized variable lying everywhere. We are not checking the validity of the pointer which we are receiving, and I mean, we should avoid it unless and until you can prove that at this particular point of time when I will receive a pointer, it will have a valid value. Use modern C++ features. For example, if you use smart pointers, there are very less chances that you will face pointer related issues. Range-based for loops will not go out of bound. Brace initialization will not go into overflow of the signed integers. Then you can use std optional instead of returning some null pointer or some dealing with some -1 0 kind of return status. Instead of using a union, you can use std variant, again very safe. Instead of using void star, you can use std, again very safe, because all the behaviors are defined very clearly, whether it will throw an exception or whether it will return a null pointer on a particular operation, very well defined in this all modern C++ features. Again, you can enable some extra compiler warnings. Don't ignore compiler warnings. Again, if there is a compiler warning, it means something. It means, so go attend that compiler warning, fix that one. Again, this I talked about, use a const expr. Use detection tools like static analysis tools, and there were some cases where your static analyzer does a very good job to detect whether there is a UB or not UB. So something like clang static analyzer or CPP check or sonar checks you can do. And at runtime also you can use some instrumentation techniques and use Valgrind, address sanitizer, or undefined behavior sanitizer. The problem with dynamic analysis tools like UBSAN is, for example, if there is an out of bound access happening, you have to write a program or test such a way that it triggers that out of bound access issue. Unless and until it doesn't trigger that out of bound access issue, sanitizers can't detect that one, right? I mean, let's say you are running some software, some test case. In that one, your test is not invoking that undefined behavior. Compiler will not able to, sorry, these tools will not be able to any help to you. So you need a really thorough testing environment here. And yeah, that's it from my side. I think I'm all within a time. So we can start with the Q&A. So let me read questions. Okay. So the first question, which is from Abhi, is, do we have the same behavior across optimization flag on slide number 20? Let me jump to slide number 20. Most probably yes, but we can't say again because it is undefined behavior. And because if it is undefined behavior, we can't say whether across the compilers version and that whether it will be same or not. It might be different. Next question. Are all these observations with default optimization flag? No. these are observations with different optimization flag enabled. And with each example I have shared, okay, whether I have enabled O1, O0, O2, O3, I have created this Godbolt links as well. So when I will share this somewhere, you can basically try out this one. We have next question. Will not UV sun raise error for this type of code? Again, I'm not saying, I'm not sure which code you're talking about here, but again, undefined behavior sanitizers might give you the results when you are running a software which triggers this undefined behavior. In other cases, it might not. For example, let's say this a plus b is less than a. We have potential undefined behavior here, but when we are using this in such a way that the inputs leads to undefined behavior. So if you are not giving input something like that a plus b, which leads into undefined behavior, UV sign is no help with this one. Why is the variable marked const expr? Is marking the function itself not enough? On slide number 38, it might not be enough because what's we say about a const expr function is that function might get evaluated into constant expression or not get evaluated at a constant expression. I mean constant time compile time. It might even get evaluated at runtime. And what it depends on in which context you are calling. So if you have some simple variable int add is equal to, and we are calling some function which is marked const expr, but compiler can see, okay, this function is not called in a const expr context, so I don't have to evaluate at constant time. So it will not evaluate that at constant time. So you need const expr at both the time, your expression and as well as the function which you are calling. Okay, will ABI leads to UB? No, not, because you don't have to deal with the ABIs. Compiler will deal with the ABIs, and compiler will make sure that, okay, whatever ABI is particularly defined for this particular platform, it is using it correctly. So I don't say that will happen. I hope we still have some time. Can take still some more questions. Okay. So I have one more question. I have seen one bug where the function has std event 32 as return type, but there wasn't any return statement in a function definition. And while calling the function, it went to infinite loop. Why is not returning from a function causing? Why is not returning from a function causing infinite loop? Okay. Again, it is undefined behavior. So what might be happening is a very simple case is when you are returning a value, it might be getting, again, this is just a assumption. It might be getting stored into a particular register, let's say EX register. And there might be some check after that return statement, after the function call, which is assuming that you will have some return value from the EX. It will check that condition, and based on that condition, there is a for loop. It might be, it can be anything. We can't say anything. Compiler even might say, okay, there is undefined behavior, I will generate some code. Doesn't matter. Okay, I think that's it from my side.